раз. Как там со звуком? Слышно что-нибудь? Вот задержка, наверное, идет. Есть? Угу. Спасибо. Okay, our first goal for today is to prove the following result, the following theorem. This is the functional modal theorem for cyclic star modules over C of x over the algebra of continuous functions on a compact Hausdorff topological space. So suppose that X is a compact Hausdorff topological space, and suppose that H is a cyclic star module over C of X. I claim that there exists a positive random measure mu, a positive random measure mu on X, such that H is unitarily isomorphic to the big O2 space over X, considered as a star module over C of X. So briefly, each cyclic star module over C of X has this form. Well, before we prove it, let's briefly recall some ingredients, some notions which appear in the statement. So let's recall, first of all, what a star module is. Well, if you have a Banach star algebra, let's suppose that it is unital Banach star algebra A. So in our case, A is C of X, but for the definition, we can take an arbitrary unital Banach star algebra. Then a star module over A is a Hilbert space H, a Hilbert space equipped with the structure of a left A module. So it has two structures, an inner product which makes it into a Hilbert space, and the left A module structure. And these structures are compatible in the sense that, first of all, the action of A on H is continuous, which is quite natural. And second, we require that the involution on A is compatible with the inner product in the sense that we have the following formula. So this is the definition of a star module. And we observed at the previous lecture that this notion is actually equivalent to the notion of a star representation. So by definition, a star representation of A on the Hilbert space H is just a unital star homomorphism from A to B of H. A unital star homomorphism. So the correspondence between star modules and star representations is very easy. If pi is a star representation, then we can define a star module structure on H by the following simple formula. And the other way around, you will have if H is a star module, then this formula determines the star representation. So star modules and star representations are just equivalent objects. The class of star modules, the class of all star modules over A, obviously forms a category. So the morphism, a morphism of star modules is just a bounded A-modular homomorphism. So that is a bounded linear operator which commutes with the action of A. And there is also special notion of a unitary isomorphism. A unitary isomorphism between two star modules is an A-module isomorphism which preserves the inner product. That is an A-module isomorphism which is a unitary operator. Well, let's also recall what cyclic means. If A is a star algebra, a bound star algebra, and H is a star module, then for each vector V and H, we can consider the so-called cyclic submodule generated by V. So by definition, this is the closure of the set of all elements of the following form. The cyclic submodule generated by V. So clearly this is the smallest closed submodule of H, which contains V. And we say that H is itself cyclic. H is cyclic if there is an element V in H which generates H in the following sense. In the sense that the cyclic submodule generated by V is equal to H. And let's also recall an example, a typical example of a cyclic module. So if X is a compact Hausdorff topological space, and the mu is a positive Radon measure, then L2, the space of square integrable functions on X, becomes a cyclic star module over C of X. The action of the algebra is just pointwise multiplication. The action is pointwise multiplication. Here A is an element in our algebra, and F is in L2. To show that it's cyclic, we just consider the function which is identically 1. It is in L2 because the measure is finite, and it's easily seen to be a cyclic vector. It is a cyclic vector because if we look at the definition of a cyclic submodule, we see that this set, before we take the closure, in this case, this set is nothing but the canonical image of C of X in L2 of X, which is dense in L2 of X. So after we take the closure, we get L2 of X. So this is a cyclic star module, and our first result for today is that every cyclic star module over C of X has this form, that it is unitarily isomorphic to L2 for a suitable positive Radon measure on X. Okay, let's now prove this result. So we choose a cyclic vector V, a cyclic vector, and we apply the Riesz-Markov-Kakutani theorem to get a measure by the Riesz-Markov-Kakutani theorem. We conclude that there is a complex Radon measure, mu, a unique complex Radon measure, such that the following number, here f is a continuous function, so we act by f on V and take the inner product with V. So clearly this is a bounded linear function on C of X. So it is given by a measure. It is determined by a measure in the sense that it is the integral of f with respect to mu. for each f in C of x. And I claim that this is exactly the measure we are looking for. First of all, we must show that mu is positive. Well, why is it positive? Well, suppose that f is a non-negative continuous function. And let g denote the square root of f, which is also a continuous function. Then, the integral of f with respect to mu is the integral of g squared, and so f is g squared, but g is positive, and in particular it is real, so we can write this in the following form. G bar is just g, because it is real. And now, since H is a star module, so we look here, we use this axiom, we take G bar from here to here, so it becomes just G. And we see that this is the inner product of GV with itself, which is clearly non-negative. So we see that our measure mu has the property that the integral of any non-negative continuous function with respect to mu is non-negative. It's a simple exercise to show that this property implies that mu is a positive measure. It's a little exercise in measure theory. Okay, so we have constructed a positive measure, a positive Rodin measure. And let's now construct a unitary isomorphism between H and L2. Actually, we'll construct a unitary isomorphism between dense submodules and then extend it by continuity. For each continuous function f on x, we use the following notation. F in square brackets will denote the equivalence class of f in L2. The equivalence class of f in L2. And we denote by E the space of all such equivalence classes. So clearly E is a dense submodule in L2. A dense submodule in L2. So to construct a unitary isomorphism between E and a suitable submodule of H, let's first perform a little calculation. So we take any two functions, f and g, any two continuous functions, and let's calculate the inner product of fv and gv. So again, we use the assumption that H is a star module, so we move G from here to here, so it becomes G bar. And by construction, this is just the integral of this function with respect to mu. G bar f, or equivalently f g bar, with respect to mu. But this is nothing but the inner product of the respective functions in the L2 space. So formally we take the equivalence classes of f and g in L2 and take their inner product. In particular, this calculation shows that the norm of Fv is equal to the L2 norm of F. We just substitute G equals F here and take the square root. So these equalities imply that we have a well-defined linear operator, a well-defined linear operator, as denoted by phi 0, from E to H, which takes the equivalence class of each continuous function, f to fv, for each continuous function f. Well, indeed, why is it well defined? We have to show that actually the right-hand side depends only on the equivalence class of f, and not on the f itself. But equivalent to this means that if this is 0, then this is also 0. But if the equivalence class of f is 0, we have 0 here and 0 here. So fv is also 0. And so this shows that phi 0 is well defined. It is well defined, clearly it is linear. And it's also clear that phi 0 is C of x modulo morphism. This is clear from the formula. Also, if we look again at this calculation, we see that phi 0 preserves the inner product. Phi 0 preserves the inner product. And finally, let's observe that its image is dense. In H. Well, indeed, the image of phi 0 is exactly the submodule algebraically generated by V. So since V was a cyclic vector for H, we conclude that this is dense in H. This is because V is a cyclic vector. And that's it. So phi 0 is a unitary isomorphism between a dense submodule in L2 and a dense submodule in H. So by continuity it extends phi 0 uniquely extends to a unitary isomorphism so unitary isomorphism phi from L2 to H. And this completes the proof. Okay. Let's now look, so our next goal will be to deduce an operator theoretic corollary of this result. So, suppose now that H is a Hilbert space, and T is a normal operator. A normal operator on H. And suppose that K is a compact subset of the convex plane, which contains the spectrum of T. Let's recall that at the previous lecture we constructed continuous functional calculus for T, gamma T. A continuous functional calculus is a unital star homomorphism from C of K to B of H. continuous functional calculus. This is a star homomorphism, a unital star homomorphism, which is uniquely determined by the following formula. It takes a little t to our operator, where little t is the inclusion map of k into the complex plane. Okay, so gamma t is a star representation of C of k. So we see that H becomes a star module over C of k by means of this representation. H becomes a star module over C of k. So explicitly f applied to V is gamma of f applied to V. And it's clear that once we have fixed k, we get a one-to-one correspondence between normal operators, T, whose spectrum is contained in K, and the class of all star modules or star representations of C of k. There is a bijection here. So we have just observed that a normal operator generates a star representation, namely the continuous functional calculus. And the other way around, if you have a star representation pi of this algebra, then we can consider the operator pi of little t, where again little t is the inclusion map. So clearly this is a one-to-one correspondence. It turns out that this representation theoretic look at operators is very useful. So the language of modules is sometimes much more flexible than the language of linear operators. We now have the following simple proposition. Now suppose that we have two normal operators, S, which is a normal operator on H1, and T, a normal operator on another Hilbert space. And suppose that K is a compact subset of the complex plane, which contains the spectrum of S and the spectrum of T. So because of this remark, we see that both H1 and H2 become star modules over C of k. H1 and H2 become star modules over C of k. So I claim that if we have a morphism, say U, from H1 to H2 is C of k module of morphism, then this operator U intertwines S and T in the following sense. U S equals T U. In particular, we see that if H1 and H2 are unitarily isomorphic as star modules over C of k, then the operators S and T are unitary equivalent. So I will use the same notation. Unitarily equivalent. Well, indeed, what are unitary equivalent operators? We say that S and T are unitarily equivalent if there is a unitary operator U from H1 to H2 which satisfies this condition. This was our initial definition of unitary equivalent operators that we have already used when we proved the Hilbert-Schmidt theorem. It can be expressed by means of the obvious commutative diagram. And so we see that indeed, if U is unitary and satisfies this condition, then S and T are unitarily equivalent. And the proof of this result is just a line. It's rather an obvious observation than a real result. Well, since U is assumed to be a C of k modular morphism, in particular, it satisfies the following condition. For each V in H1. But what is this? The left-hand side can be written as follows. So little t acts on H1 as the operator S. So this is U as V. And here we act by the same function t on a vector belonging to H2. And C of k, again, the C of k acts on H2 by means of the functional calculus of t, and in particular, little t acts on H2 as the operator big T. And that's it. So we see that US equals TU. That is, U intertwines S and T. Okay. In fact, the converse is also true. I'll not prove this result, but just for your information. If U satisfies this condition, then U is a C of k modular morphism. This follows from, actually this is an equivalent form of a classic theorem of Fogarty and Putnam. Well, actually, their theorem is usually stated in slightly different terms. It states that if U intertwines S and T, then the same operator U intertwines S star and T star. And by using this, we can easily deduce that U is a C of k modular morphism. I'll not prove this result, but instead of that, I suggest you the following simple exercise. Prove the right to left implication, assuming that S and T are self-adjoint. For self-adjoint operators, S and T. This is rather easy. Just a simple application of the Stone-Weierstrass theorem. Okay, let's now introduce operators which correspond to cyclic modules over C of k. So we have the following definition. Suppose that H is a Hilbert space and T is a bounded linear operator on H. We say that T is star cyclic if there exists a vector V in H such that the following linear span, the closure of the linear span of all vectors of the following form over all non-negative integers n and m is equal to h. So what is this? Actually, it's easy to see that the closure of this linear span is the smallest closed subspace, which contains V and which is invariant under both T and T star. So if this subspace is equal to H, then we say that T is a star cyclic operator. And we also say that T is cyclic if we can remove T star from here. As if there is V in H such that the closure of the linear span of all elements T to the power mv, where n runs over non-negative integers, is equal to H. And each such vector V is called a star cyclic, or respectively a cyclic vector. Each such V is a star cyclic, respectively cyclic vector. For T. Okay, it's immediate from the definition. Let's observe that, of course, each cyclic operator is star cyclic. In general, the converse is not true, but the converse is obviously true for self-adjoint operators. For self-adjoint operators, these two notions are equivalent. In fact, it turns out that these two notions are also equivalent for normal operators. This is not obvious at all, but this is a rather deep theorem due to James Brown. So we have the following fact. 1955. If T is normal and star cyclic, then it is already cyclic. We will not prove this result. The proof is rather non-trivial, but at least the statement is useful. But we will not use it. Instead of this, we will work with star cyclic operators on a Hilbert space. And now we have the following simple relation between star cyclic operators, star cyclic normal operators, and cyclic star modules. Another proposition. So let it be proposition 1, and this is proposition 2. Suppose that H, again H is Hilbert space, and T is a normal operator on H. So I claim that T is a star cyclic operator. T is star cyclic, even only if H, considered as a CFK module, by means of this correspondence, is cyclic. H is cyclic star module over C of K. Whereas before, K is any compact subset of the complex plane containing the spectrum. Compact set containing the spectrum. To prove this result, we simply we simply apply the Stone-Weierstrass theorem once again. Well, indeed, if you take the subalgebra of C of k, the subalgebra of C of k, generated by the function which is identically 1, level t, and the complex conjugate of t. So this subalgebra is dense in C of k. We have already used this fact when we proved the uniqueness of the functional calculus. And this is indeed true by the Stone-Weierstrass theorem. If we now look at the definition of a star cyclic operator, so we look at this vector subspace of H, we see that for each vector V, this subspace t to the power m, t star to the power m, V, where n and m run over the negative integers. So this space is nothing but the cyclic submodule of H generated by V. Why is it so? Well, what is this? This is this vector is a monomial of two variables applied to t and t bar, and then applied to V. So this before we take a closure of this linear span, we get the cyclic submodule of H. Not over C of k, but over the polynomial algebra in two variables, algebraically generated by V. But since this polynomial subalgebra is dense in C of k, and since we take the closure, we can replace this polynomial algebra by the algebra of all continuous functions, and we get this equation. We get this equality. And that's it. So the operator is star cyclic if and only if this subspace is equal to H for a suitable V. And similarly, H is a cyclic module if and only if this is equal to H for a suitable V. And now combining all these results, we get theorem 2, which is actually a special case of theorem 1. This is the functional modal theorem. Functional model for star cyclic normal operators. Well, probably before we state this result, let me give an example of a star cyclic operator. And at the same time, we will introduce some notation. So suppose that K is a compact subset of the complex plane. K is a compact subset of the complex plane, and mu is a positive Radon measure on K. A positive Radon measure. And consider the following operator. I denoted this operator by MT. It acts on the big O2 space. And it acts as multiplication by the coordinate. It takes f of z to zf of z. So it's easy to see that this is a star cyclic normal operator. MT is a star cyclic normal operator. Why is it star cyclic? Well, the function which is identically 1 is a star cyclic vector. is a star cyclic vector, because if we look at the definition of a star cyclic vector, we see that if we apply this our operator to V, which is identical to 1, what we get here, the linear span, is just the space of polynomials in T and T bar, which is dense in C of k, and so therefore it is dense in L2, because C of k is dense in L2. So it is indeed a star cyclic vector. And now applying theorem 1, we get a useful special case, which is called the functional modal theorem for star cyclic normal operators. Functional model for star cyclic normal operators. It states that actually each star cyclic normal operator has the form described in this example. So if T is a star cyclic normal operator on the Hilbert space H, then there exists a positive random measure on the spectrum, positive random measure on the spectrum, such that T is unitarily equivalent to the operator MT described in this example, and acting on the big O2 space on the spectrum with respect to the measure mu. So every star cyclic normal operator is unitarily equivalent to the multiplication operator of this simple form. And the proof is just a combination of theorem 1 and propositions 1 and 2. Well, indeed, H becomes a star module over the algebra of continuous functions on the spectrum. This star module is cyclic by proposition 2. And we apply theorem 1, and we see that H is unitarily isomorphic to L2 of sigma mu. But now proposition 1 implies that the operator itself, the operator T, is unitarily equivalent to multiplication by the coordinate. And that's it. Okay, so now we proved our functional modal theorem for cyclic star modules and for star cyclic normal operators. Our next goal will be to extend it to arbitrary star modules, not necessarily cyclic, and respectively to arbitrary normal operators. And before we can do it, let's discuss some general constructions. Some constructions. Suppose that we have a family of Hilbert spaces, Hi. A family of Hilbert spaces. And let's denote by H the set of those elements in their product, Vi, in the product of these spaces, such that the following sum is finite. Probably I have to explain what this sum means, because I don't assume that I is countable. Well, if I is countable, then of course this sum is already defined. This is just the sum of a series. And in the general case, we define the sum to be the supremum of the sums taken over all finite subsets of I. The supremum is taken over all finite subsets J of I. So clearly, if I is countable, then this definition is equivalent to the usual definition of the sum of a series. So here's a useful and rather simple exercise. First of all, I claim that if the this is V, of course, Vi. First of all, I claim that if this condition is satisfied, that is, if this sum is finite, if this sum is finite, then actually Vi is 0 for all but countably many indices. So, in some sense, the support of this family Vi is at most countable. And so eventually everything reduces to the sum of a series. And the second exercise, if we look at this set H, I claim that H is not just a set. H is, first of all, it's vector subspace of the product. Vector subspace of the product. And moreover, it has a canonical structure of a Hilbert space, which is a Hilbert space with respect to the following inner product. If U and V are two elements of H, which are square-summable families in the product, then we define the inner product to be the sum of the inner products of the components. Let's note that since we have we already suppose that we have already proved part 1, so both U and V are concentrated on countable subsets, so we can assume that they are both concentrated on the same countable subset. And so the meaning of this formula is just the usual sum of the respective series. Okay, so this is a simple exercise. First of all, you have to show that this is well defined, of course, that the right-hand side converges. This is simple application of the Cauchy-Brunikovsky inequality. And the completeness of this space, the completeness is proved in exactly the same way as the completeness of the little L2 space. Exactly the same argument which works for the little L2 space shows that this space H is complete. Actually, if in a special case where all the summands are one-dimensional, all the spaces Hi are one-dimensional, and big I is countable, what we get is exactly the little L2 space. And there is a special name for this H. H is denoted by the following symbol. So we use the usual direct sum notation, and we put a dot over the direct sum sign in order to distinguish between the algebraic direct sum and this construction. And it is called the Hilbert direct sum of our family. It's called the Hilbert direct sum of our family Hi. Okay, so now let's apply our construction to star modules. Let's now observe that if each Hi is not just a Hilbert space, but is a star module, over some Banach star algebra, over a unital one star algebra A, then their Hilbert direct sum is also a star module in a natural way. H is also a star module over A, with respect to the following obvious action. The action way is just component-wise. So you have a square integrable family Vi, then the action of an element little a on our family is the family with components A, Vi. Let's observe that this new family, AVI, is also square integrable. So this is well defined. Why is square integrable? Let's recall that the norm, let me write this down explicitly, the norm of AVI satisfies the sum-multiplicative inequality. So this is well defined because I have the following inequality, which was already discussed at the previous lecture, and which is equivalent to the fact that each star representation, the norm of each star representation is less than or equal to 1. So this inequality obviously implies that if Vi is square integrable, that is, Vi sits in the Hilbert direct sum, then this is also square integrable. And all the axioms of a star module are easily verified. And the second observation gives us some useful condition under which a given star module is isomorphic to a Hilbert direct sum of its submodules. So suppose now that H prime is some star module. H prime is a star module over A. And suppose that we have a family Hi, a family of closed pairwise orthogonal submodules of H. And let's also assume that the algebraic sum is dense in H, such that the sum of this family is dense in H. In this case, we have a map that's denoted by, well, actually, we don't need any special notation for this map. This map acts from the algebraic direct sum of our family to H prime, Oh, sorry, I forgot to put the prime here, of course, H prime. We don't have H, we have only H prime. So this map takes a family in the algebraic direct sum. And by the way, let's recall that the algebraic direct sum consists of all finitely supported families. So this family is finitely supported, and our map takes this family just to the sum of this family, which is actually finite. So we observe that this map is obviously an A-module morphism. Because each Hi is a submodule in H prime. And it preserves the inner product. Preserves the inner product. This follows from the assumption that our submodules are pairwise orthogonal. So when we write explicitly the inner product of two such finite sums, say xi and yi, we see that their inner product is given by this formula. for the simple reason that they are orthogonal to each other. Or maybe, since I wrote before Vi, let it be Vi also. We are mostly interested in the case where our Banach algebra is the algebra of continuous functions, and the letter little x will be used for the points of our space. And a little v will be used for the vectors in our Hilbert space. Okay, so this map is an M-model morphism. It preserves the inner product, and its image is dense. Its image is dense in H prime by assumption. And so this implies that this map extends to a unitary isomorphism. This map uniquely extends to unitary isomorphism between the Hilbert direct sum of our family. I put the dot over the direct sum sign to H prime. So in summary, once we have a family of closed pairwise orthogonal submodules of a given module H prime, such that their sum is dense, we immediately get a unitary isomorphism between the Hilbert direct sum, this is the module of all square summable families, and H prime. Okay, let's now prove two useful lemmas about star modules. Lemma 1. Suppose that A is any unit of Banach star algebra, and H is a star module over A. And suppose that we have a submodule, H0. Submodule. I claim that the orthogonal complement is also a submodule. The orthogonal complement of H0 is also a submodule of H. This is quite useful because once we have a closed submodule, we immediately get a direct sum decomposition into two submodules, the submodule and the orthogonal complement. And the proof is just a line. We take any element A in A, and element U in the orthogonal complement, and an arbitrary element V in H0. And consider the following inner product, AU and V. We want to show that this is 0. This will mean that AU belongs to the orthogonal complement, and so the orthogonal complement will be submodule. But this is equal to the inner product of U and A star V. And A star V belongs to H0, because H0 is assumed to be submodule. And now since U is in the orthogonal complement, this is 0. And so this implies that AU belongs to the orthogonal complement. And that's it. So the orthogonal complement of a submodule is also a submodule. And lemma 2, which essentially shows that each star module, or any Banach star algebra, is isomorphic to Hilbert direct sum of cyclic modules. Again, A is a unit of Banach star algebra, and H is a star module over A. Then there exists a family HI of pairwise orthogonal cyclic submodules. Cyclic submodules of H. Such that H is unitarily isomorphic to their Hilbert direct sum. So this enables us to reduce arbitrary star modules to cyclic star modules. And the proof is a standard application of Zorn's lemma. So let's denote by M the set whose elements are families of non-zero, pairwise orthogonal, cyclic submodules of H. M becomes a partially ordered set. The order relation is just the inclusion. And it's easily seen that this set satisfies the condition of Zorn's lemma. This is a simple exercise for you. This is more or less immediate. Once we have a chain of such families, to get an upper bound, we just take the union of this chain. And what we get is an upper bound. So each chain has an upper bound, and so the conditions of Zorn's lemma are satisfied, and thus we have a maximal element. There exists a maximal element. Let's denote this family by HI of M. And I claim that this is exactly the family we are looking for. To construct such an isomorphism, let's come back to this observation. So we exactly in this setting as here, so we have a family of closed pairwise orthogonal submodules of H. The only thing we have to show is this density condition. So now we have to show that the algebraic sum of this family is dense in H. So let's denote by H0 the closure of their sum. And suppose that this is strictly smaller than H. Well, it's a closed vector subspace, so this implies that the orthogonal complement is non-trivial. So we can find a non-zero vector, little v, belonging to the orthogonal complement. And now to get a contradiction, we construct a bigger family, a strictly bigger family of pairwise orthogonal cyclic submodules. To construct it, we simply add a single element, namely the cyclic submodule generated by V. So we consider the same family HI, and we add the cyclic submodule generated by V. And this new family belongs to M by lemma 1. Well, indeed, we have to show that it is pairwise orthogonal, but V is in the orthogonal complement, and the orthogonal complement is a submodule. So, since the orthogonal complement of 3.0 is submodule, we see that this cyclic submodule is contained in the orthogonal complement as well, in the orthogonal complement to H0. And so it is orthogonal to each HI. So this new bigger family is also an element of M, which is strictly bigger than HI. And this is a contradiction. a contradiction with the maximality or the original family Hi. So this contradiction implies that actually H0 is equal to H. And applying this observation, observation 2, we conclude that H is unitarily isomorphic to the Hilbert direct sum of our family. Okay, now we eventually came to the functional model theorem for arbitrary star modules over C of X.
I have a question.
Yeah.
So, did I understand that correctly that on M we have just set theoretical order, like on the families of non-zero pairwise orthogonal cyclic modules? So we have just a set theoretical order, like.
If we have two families of such submodules, we consider them as just two sets of submodules, and one set is bigger if it contains the smaller one. So this is just the inclusion. So this one clearly contains this one. So it is bigger in the sense of our order relation. And so this is impossible by assumption. That's the point. Okay, before we prove the functional model theorem, let's recall some notation from the previous lecture. Suppose we have a measure space, omega A mu, a measure space, not necessarily finite, and actually not necessarily sigma finite. And suppose we have a compact Hausdorff topological space X. And suppose that phi is a measurable map from omega to X. Here by measurable I mean that it is measurable with respect to the Borel sigma algebra of X. That is, the preimage of every Borel set in X belongs to the sigma algebra A. We go to space over omega, L2 of omega mu becomes a star module over C of X. With respect to the following action. If A is a continuous function on X and F is a square integrable function on omega, then A dot F is the pointwise product of A composed with phi and F. So A composed with phi becomes a bounded measurable function on omega, and we just take the pointwise product of this bounded measurable function with F. The pointwise product of a bounded measurable function and a square integrable function is, of course, square integrable. So this construction was discussed at the previous lecture, and we introduce the following special notation for this module. So this module will be denoted by L2 of omega mu phi. So the module structure is determined by phi. We now have the following theorem, which gives us functional model for an arbitrary star modules over C of X. So if X is a compact Hausdorff topological space, and H is a star module over C of X. Then there exists a measure space, omega A mu. So omega is a set, A is a sigma algebra, and mu is a measure. And there exists a measurable map phi from x to from omega to x, such that H is unitarily isomorphic to this concrete module, L2 of omega mu phi. In other words, this example of a star module actually gives us the general case of a star module. So any star module has this form, up to unitary isomorphism. The idea of the proof is as follows. We first of all decompose H into a sum of into a Hilbert direct sum of cyclic summons by using lemma 2. Then we take a functional model for each of the summons, which exists by theorem 1, and then we somehow patch together these functional models to get our measure space omega mu. So this is the idea. And here is a formal proof. So, first of all, we combine theorem 1 and lemma 2, and we see that H is unitarily isomorphic to the Hilbert direct sum of a family of the following modules: L2 of X mu I, where mu I is a family of positive random measure, or some family mu I of positive random measures on X. So we decompose H into a Hilbert direct sum of cyclic submodules and take the functional model for each of these cyclic submodules. And now we somehow patch together these measure spaces. So first of all, we construct omega. Set omega will be just the product of X and I. And sometimes it is convenient to look at the set as the disjoint union of many copies of X. The disjoint union of Xi, where each Xi is equal to X. This is another way of looking at the direct product. Okay, so this is our omega. Now we have to define A, the sigma algebra A. Well, we define the sigma algebra A as follows. It consists of all disjoint unions of Borel subsets of Xi for each I. The I is a Borel subset of Xi. And this is easily seen to be a sigma algebra of omega. Well, now we have to define a measure on A. And we define the measure of each such set of such a disjoint union should be the sum of the measures of the sets bi, mu I of bi over all I. Of course, I don't claim that this is always finite. In general, this is not the case. But nevertheless, we get sigma. It is easy to see that we get a sigma additive positive measure on A. So we get a measure space. Omega A mu is a measure space. Okay, now the next step is to construct a measurable map phi from omega to x. And this is very easy. This is just the projection. If we now interpret omega as the direct product, we just take the projection over x. Phi acts from omega to x by the following formula. It takes each pair xi to x. If we look at the definition of our sigma algebra A, we can easily see that phi is clearly measurable. Okay. By the way, here's a useful picture, which is useful to keep in mind when we work with this object. So if we, for example, we suppose that I is countable and and x is just a unit interval of the real line, then this is the picture which represents omega. It consists of infinitely many intervals. x1 is x equipped with the measure mu1, x2 is x equipped with the measure mu2, and so on. And the function phi has the following graph. And so, this is the picture which represents our measure space and our function phi. Okay, now we have to construct a unitary isomorphism between H and this modulo L2 of omega mu. To construct this isomorphism, let's introduce some notation. Let Hi denote the set of those elements F in L2 of omega, L2 omega mu, which are concentrated on the ith space in this union. So formally this means that F vanishes almost everywhere on the complement of xi, omega minus xi. And it's easy to see that Hi is actually unitarily isomorphic to L2 of x equipped with the measure xi. Now, this is a little exercise, but the isomorphism is more or less obvious. The isomorphism is just extension by zero. So once we have a square integrable function on x, we take the ith copy of x in this union, the ith copy. F is already defined on this copy, and we let it equal to 0 on the complement. And this is easily seen to be a unitary isomorphism of C of x modulus. Okay, so clearly all these submodules Hi are priori orthogonal. Hi is easily seen to be orthogonal to Hj whenever I is not equal to j. This is clear from the construction because the sets xi are disjoint. And let's show that the sum of these submodules Hi is dense and L2 of omega. Oh, well, if we have a function f which is orthogonal to each Hi, what does that mean? Well, first of all, it means that if we fix little I, that means that our function is orthogonal to all such functions which are concentrated on xi. But this means that f is actually vanishes on xi. Then f vanishes mu almost everywhere on xi. And this happens for each I. For each I. If we now look again at the definition of our measure, this is the definition, we see that this implies that f is 0 almost everywhere. F vanishes almost everywhere with respect to the measure mu. And so, this implies that the orthogonal complement to the sum of our family HI is trivial. Or in other words, this means that this sum is dense in L2. This implies that the sum of the family HI is dense in L2 of omega. Okay, now the last line of the proof. So since this is a family HI, this is a family of pairwise orthogonal submodules of L2 of omega mu, whose sum is dense in this module, we conclude that L2 is unitarily isomorphic to the Hilbert direct sum. Okay, but we already know that each HI is unitarily isomorphic to L2 of x equipped with the measure mu I. So we have the following isomorphism. But if we look now at the beginning of the proof, we see that this direct sum is unitarily isomorphic to H. And this is the end of the proof. So we have constructed a unitary isomorphism between H and L2 of omega mu. Well, maybe the proof is a little bit abstract, but here's the picture which explains the basic idea. So this picture shows that to get the functional model for H, we simply decompose it into cyclic summons, consider a function model for each of the summons, and then patch them together as shown on the picture. And as a corollary, we get a special case for normal operators. Theorem 4. This is functional model for a normal operator. And this is our first form of the spectral theorem. Spectral theorem 1. Suppose that H is what's Hilbert space, and T is a bounded normal operator on H. Then there exists a measure space, omega A mu, and a bounded measurable function phi, a complex valued function on omega, which actually takes omega to the spectrum of our operator, such that T is unitarily equivalent to the multiplication operator m phi acting on the L2 space. So it acts as multiplication by phi. So this is our functional model. So we see that each bounded normal operator is unitarily equivalent to the multiplication operator on a suitable two space. In the general case, omega and mu is an arbitrary measure space, so I don't claim that it is finite, and I don't claim that it is sigma finite. But in the important special case where H is separable, we can say more, and this is a little exercise for you. If H is separable, then we can take, for omega, we can take just a real line. And we can construct our measure mu in such a way that it is finite. Find the measure mu such that mu is a finite radial measure on the line. Well, maybe let's also assume for simplicity that T is self-adjoint. T is self-adjoint. In fact, this is not necessary, but this makes the proof more transparent. And here is a hint. Our family I will be necessarily countable because of the separability assumption. And each xi is a subset of the real line. So we just put them together consequently on the real line, and we get our measure space omega. Okay, so this is one of the most popular form of the spectral theorem. It has the advantage of being very concrete and understandable, in the sense that the statement of this theorem is quite easy to understand. And in fact, all the essential information about our normal operator is contained in its functional model. The only disadvantage of this form of a spectral theorem is that the functional model is not canonical in any reasonable sense. And the reason is that if we look at the proof, to construct omega we used a direct sum decomposition of H into cyclic submodules. And this decomposition is not unique in any reasonable sense. And this implies that the functional model is not canonical, but it is nevertheless very useful. And in the remaining lectures we discuss some other forms of the spectral theorem, which are maybe not so transparent, but which have the advantage of being canonical. Thank you.